Right. Good morning, everybody. I'm Ekhlas from University of Georgia, and I'll be presenting my paper on individual planning in agent populations, exploiting anonymity and frame action hypergraphs. The work was done in collaboration with Yingke, Chen and Prashant, Doshi. So our planning problem deals with coming up with optimal plan for an individual agent who is operating in partially observable stochastic settings in presence of other self-interested agents whose preferences and goals may not necessarily align with the preferences and goals of our agent. So such planning problems are formalized by interactive POMDPs, which are a generalization of POMDPs to multi-agent settings. They differ from cooperative planning because we don't have an assumption of a common prior or common common payoff. In recent times, I-POMDPs have been explored by several researchers as a viable framework for solving many real-world problems, such as money laundering, playing Kriegspiel and limited stand game, modeling human strategic behavior in defense for simulations and controlling autonomous AUVs, and also for teaching robot from human teachers. So the brief overview of problem is such: we have our agent, the subject agent, agent 0, for whom we are trying to compute an optimal plan. The agent acts, it performs actions which alters the state of the environment given here as S stochastically, and as a result it gets an observation which may have some uncertainty associated with it, and it gets a reward. Now there may be other agents present in the environment, up to n agents, 1 through n, whose goals does not necessarily aren't necessarily the same as our agent, and they are also operating in a similar way. They perform actions, and their actions have a similar have some effect on the environment, and they too receive an observation and rewards according to their goals. Such planning problems are captured by I-POMDPs, which is represented by this tuple. It is pretty much the same as POMDP tuple. The difference being, instead of physical states, we have interactive states, and we have the joint actions of all agents. Since we don't really control the policy of the other agent, we don't decide what the other agent would perform, what actions they would perform. But however, we still need to predict what the other agent does over a period of time in order to compute an optimal plan for ourselves. So how do we do that? In order to do that, we have a set of models for each agent, and these models tell us how the agent would act over a period of time. While we are modeling the other agent, we could either model it as acting according to some simple rules like tit for tat, or following a constant static probability distribution over actions. Such kind of modeling is known as subintentional modeling. Or we could model the other agent as an intelligent agent who is planning for itself, who operates in a similar manner as we do. And such kind of modeling is known as intentional modeling. An intentional modeling model of the other agent consists of its belief and its frame. The frame tells us what the preferences and the goals of the other agents are. Typically, I-POMDPs model the other agent as other agents as I-POMDPs themselves. So if the other agent is I-POMDPs, it is very much likely that they are modeling our agent as well. So modeling boils down to what I think the other agent thinks, what I think, and so on and so forth. That could go on until infinity. But solution to infinitely nested I-POMDPs are infeasible. So we restrict ourselves to finitely nested I-POMDPs. And the level of nesting is given as L. So level L I-POMDP models the other agent as a level L minus 1 I-POMDP, and so on till level 0, which is basically a POMDP, and that models the other agent as static noise in the environment. The transition, observation, and reward functions are dependent on the joint actions of all agents. Because of partial observability, we maintain a belief, which is a probability distribution over the interactive state space. Our goal is to compute a policy, which is a mapping from belief to a distribution over actions. and we want to compute a policy that would optimize the rewards of our own subject agent, agent 0. Okay, so two basic functions that we perform for I-POMDP solution, same as for POMDP solution, are belief update and value function. A belief update updates the probability distribution over the interactive state space, and it can be broken down into update of belief over the physical state space, which tells us how the state of the environment evolves over a period of time, and update over the models of the other agent, which tells us how the behavior of the other agent changes over a period of time. Then there is value function, which computes optimal long-term reward for agent 0, and it incorporates the belief update in its computations. Okay, computing I-POMDPs have many sources of interactability, which are termed as curses. And some of the curses are curses of dimensionality and curses of history, which are inherited from POMDP itself. Curse of dimensionality is the effect of the size of the state space. Curse of history stems from partial observability, and it's the exponentially growing size of solution. In multi-agent settings, particularly I-POMDP, we have curse of agent modeling, which is an effect of curse of history on curse of dimensionality, because due to curse of history, the number of reachable models of the other agent also grows exponentially, which further worsens the dimensionality of our interactive state space. But in this paper, we are focusing on curse of many agents, which is exponential growth in the size of joint action space and joint model space with number of agents. So this curse is very prominent in multi-agent decision making, which we can see here. Let's consider a very simple case where every other agent has only 2 actions. If we had 10 agents, we are considering over 1,000 actions. If we had 30 agents, we are considering over 1 billion actions. And if there are 1,000 agents, we have to consider over 10 to the power 300 joint action, which is just infeasible. There is no way we can solve I-POMDPs by this representation. How does this representation manifest? Well, because of exponentially growing joint action and joint model space, we face memory problems because these table transition, observation, and reward function depend on the joint action. Similarly, the belief space is a distribution over the interactive state space, which contains the joint model space, and representing these values becomes harder. Then there is cost of computation, because in order to compute belief update and value iteration, we still need to iterate over all joint actions, and that is time consuming over here. Due to these problems, traditional approaches don't scale to more than 5 agents, but our target was to solve I-POMDPs for over 1,000 agents. So before we go into how we solve the problem, let's look at a problem domain that we took as an example and try to solve that, which could potentially have more than 1,000 agents. We focus on the policing protest problem. Police force is tasked to maintain peace at 3 locations or 3 sites, which are shown here. The police, which is agent 0, has 2 troops, which it could send both of them to one location, or it could split up and send it to 2 different locations. There are N protesters who can decide to go to one of these 3 locations and protest there, or they could decide to stay out of protest all total. The protest intensity and rewards are affected by the number of protesters at a site and number of police troops present to control the protesters at that site. So now going into how we solve this problem. First, the problem of representing the belief. Exponential space required, infeasible. So what we did was we made an assumption that models of different agents are conditionally independent of each other given the physical states. So what we could do is we could break our belief into these factors. We have one distribution over the physical state space and one conditional distribution for the models of each agent given the states, given the physical states. We have also proposed a belief update which will preserve this factored representation of belief. We have one update over the physical state space, and we have update over the models of each agent given this physical state. And for each agent, we do the update separately. Next, we've exploited some more structures. We drew a lot of ideas from game theory literature, particularly action graph games. So the idea is this, that the transition, observation, and rewards in this case don't depend on the identities of agents that are performing some action, but they only depend on the number of agents that are performing an action. So such structure is called anonymity. And when we have anonymity, we don't really need to consider all joint actions independently. We could consider only configurations, which is a configuration is a tuple with the action counts for each agent. So if we can see here, this is an example for 5 protester problem. We can see all 3 of these joint action have the same action count for for different actions. We have 2 agents going to site 0, 2 agents protesting at site 1, and 1 agent protesting at site 2. So what this tells us is that joint action space contains a lot of extraneous information that is not at all required in order to solve these I-POMDPs. Next, I-POMDPs also allow different agents to have different frame, and depending on the frame of the agent, their impact may be different. For example, police response is decided by how many disruptive or peaceful agents are present at each site, where disruptive agent will have more effect on the protest and the rewards than the peaceful agent. So our configuration is modified to have count over the frame action pair and not just actions. So what it does is instead of, if we were dealing with joint action, we would have an exponential number of joint actions over here, but by exploiting configuration, we have only a polynomial number of configurations. Okay, this is a question that we face all the time. If we have anonymity, why do we model each agent individually? Because they are individual agents, and we still need to compute what action they would be performing individually. And once we have computed the action, the action of the other agent, we can then map it to configuration and use the configuration for our computations. Second, after this, we exploited the polynomial we had could still have a large exponent, but we want to make it further smaller. So what we did was we exploited context-specific independence. Intensity at a given site is unaffected by the number of protesters protesting at some other site. So when we are dealing with site 0, we don't really need action counts over protester going to site 1 and site 2. This is known as context-specific independence. To do this, first we defined context for reward function, transition function, and observation functions. And these are basically the part of the function excluding the actions of the other agent. We capture context-specific independence using frame action graph, which is a 3 uniform hypergraph. And this is a Levi representation for the reward frame action graph. This hyper edge over here tells us that when we are considering this context, we need to have configuration over frame theta j2 and action theta j1 and action aj2. So what it tells us is the value of a frame depends on configuration only over its neighbors, and all its non-neighbors may be combined together as null action, and they can be ignored when we are performing actions. This further reduces configuration space to this polynomial, where this value here, nu star, is the maximum cardinality of the neighborhood for any context. After doing this, our transition function, observation function, and reward function becomes much more context compact, and we have only a polynomial size representation. In computation, we iterate only over the configuration, not over the joint actions and joint model space. So that saves a lot of time. However, we still need to compute distribution over the configuration. So we use a dynamic programming approach, which solves the model of, given the belief, it solves the model of every agent and computes a configuration from the predicted action of each individual agents. And we have a probability, we get a probability distribution over those configuration as an output. In experiments, what we did for small problems, when there were few other agents involved, we compared the value of our approach, which is many agent I-POMDP, with the traditional I-POMDP, and for smaller agent, we could solve it exactly, which is what the expected values show here, that they were the same for both approaches. You can see that for 2 agent, it doesn't make much of a difference, but as the number of agent grows, the time taken by traditional I-POMDPs grows very rapidly, but for many agent I-POMDP, it is much more manageable. For larger problem, we found that curse of history was becoming more prominent, so we utilized observation sampling, and that gave us some savings. Here we have shown the time taken for solving up to 1,500 agents with observation sampling, and up to 1,000 agents without observation sampling. We can see that for up to 500 agents, we took around 3,000 seconds, around an hour without observation sampling. That is an exact solution. And then we have, in this slide, what we are showing is the time taken to solve 3 and 4 horizon problem with observation sampling. The key thing to notice here is the quadratic growth in time taken with number of agents, because our cardinality nu star was 2 in this case, and that is confirmed by this graph over here. In conclusion, we have exploited structure to solve many planning problem for many agents settings. We expanded the work of action graph games by Jiang and Leighton Brown. We introduced the frame action hypergraph for representing context-specific independence. We showed that many agent I-POMDP scaled to more than 1,000 agents in around 6 hours, which is a significant result. And in future, we are exploring how to better address the curse of history, which becomes prominent when there are more agents. Thank you. I have a poster outside the door, and if anyone has any more questions, I'll take them now.